Hello everyone. In this lecture we will discuss electrostatic boundary conditions. So here the electric field always undergoes a discontinuity at the boundary when we cross a surface. So here we are interested to find the change in electric field at the boundary. Okay, so suppose here we have a surface and a charge is sigma, and here suppose we have this is a Gaussian pillbox. This is above the surface and this dotted line shows below the surface, and suppose A is the area of this pillbox and the thickness of this pillbox is epsilon. In this case here we will discuss first perpendicular component, that is suppose here we have a electric field. This is above the surface, and here we have another electric field that is below the surface. Now here E perpendicular above and E perpendicular below, they are just E perpendicular above is just above the surface and E perpendicular below is just below the surface. So here according to Gauss law, E dot dA is equals to 1 over epsilon naught total charge enclosed. So here in case of a surface, sigma is the surface charge density and A is the area of the pillbox, so we can write 1 over epsilon naught sigma A. Okay, so here the thickness of this pillbox is epsilon. So epsilon is approaches to 0, that is the thickness or sides of pillbox will not contribute in the total flux because this approaches to 0. So we can write here, that is E perpendicular above minus E perpendicular below is equals to sigma over epsilon naught. Okay, so here in this case it means the perpendicular component of electric field discontinuous by an amount of sigma over epsilon naught at any boundary. Okay, So the perpendicular component of electric field discontinuous by an amount of sigma over epsilon naught at any boundary. So this is the case when we have a perpendicular component. Similarly, when we have a parallel component, then in case of a parallel component, again we have a pillbox, and here we have a component that is E above parallel, and this is E below parallel. Again we have a sigma is a surface charge here. So in this case, again E above parallel is equals to E below parallel, but at the boundary E above parallel minus E below parallel, again this is equals to sigma over epsilon naught, and here we have a n cap. So here n cap is a unit vector perpendicular to the surface. Okay, so when we couple these two, that is both the components, that is perpendicular and the parallel components, in both the cases E above minus E below is equals to sigma over epsilon naught n cap. Okay, so this is the case when we have a electric field perpendicular or electric field parallel. Then we have a, in case of a potential, the potential is always continuous across any boundary. That is, V above is equals to V below. Further, but E, that is electric field, is equals to minus del V, that is gradient of the scalar potential. So del V above minus del V below, this is equals to minus sigma over epsilon naught n cap. So in case of electric field for perpendicular component and parallel component, discontinuity is equals to sigma over epsilon naught n cap, and in case of a del V above minus del V below, this is equals to minus sigma over epsilon naught n cap. So here we have one important point. Here we have to note that these boundary conditions relates the fields and potential just above and just below the surface. So this is a very important point, that is, these boundary conditions relate the fields and potential both just above and just below the surface. Okay, thank you.